Perfect. Today we're going to finish talking about geologic time in a relatively quick fashion and then look at the things that will be on the exam that we have on Friday. Remember, there is a homework due tonight. If you have questions, anyone have questions they want to ask right now? Ivy does. What would you like to ask, Ivy?
Number 4.
What does it ask?
The San Andreas Fault separates the northwest moving Pacific plate on which Los Angeles sits from the North American plate on which San Francisco sits. If the plates lie past each other at a rate of 3.5 centimeters per year, how long will it take for the two cities to form one large city? And it says the present distance between Los Angeles and San Francisco is 600 kilometers.
Okay. So this is a question that's simply asking you to relate speed and time. It's putting a real thing, something we talked about, someday Los Angeles will be neighbor with San Francisco, into perspective. And I've said it's going to take a very long time. Well, this is asking us to actually find it. So we have a speed of 3.5 centimeters per year. We have a distance of 600 kilometers. What's the relationship between speed, distance, and time? Or what is speed? This goes back to physics, of course. Velocity has direction, speed doesn't. The rate at which it moves, that is the distance per unit time. The moves is what tells us it's distant. Rate is what tells us it's per time. So it's distance over time. Now we're trying to solve this for time, so we have to use our math skills to solve this equation for time. So I'll multiply both sides by time to get it on top because it's in the bottom. And then I'll divide both sides by speed to get speed away from time. And then with that, you can see the canceling. Speed cancels with speed, time cancels with time. And I have time equals distance over speed is equal to 600 kilometers divided by 3.5 centimeters per year. We have two different prefixes for distance, kilo and centi. What does kilo mean? 1,000. So that's equal to 600,000 meters. And what does centi mean? 1/100th. So over 0.035 meters per year. Now my meters will cancel, and I take 600,000 divided by 0.035, and I'm going to leave it to you to do that calculation. What are the units going to be? Years, that's right. Years, because we have units of 1 divided by 1 over years. 1 divided by 1 over means the thing that's on the bottom comes back up to the top. And so you're going to have something that's going to be clearly in the ballpark of just under 2 million years. No. Yeah.
If we get a decimal, do we just add 1 more year?
If you get a decimal, do you add a year? I'm not sure what you meant by that. Oh, yeah. You only have 2 digits in that rate. So all you need is 2 digits, and then the rest zeros. Okay, Danny, what did you want to ask about?
The salt doesn't evaporate over the ocean.
Okay. The question is, we have the ocean is salt water. Why is it pure water that evaporates and not salt water? So that's actually a good chemistry question, right? We just had one with physics, now we have one with chemistry. You have different temperatures at which different materials will go into the vapor phase. And so that was, remember we talked about fractioning of oil, how they separated the kerosene from the gasoline from the oil we use, for lubrication. It's the same type of thing. Salt has a much higher temperature where it goes into vapor than water. And so when you have molecules that are breaking free from the surface, it's going to be the water ones that are breaking free going into vapor. And so it's a way of separating and purifying. It's purifying in every way like it still purifies. Okay, now that we're all here that's going to be here, let's start with our actual lecture. So we're talking about the geologic time scales, time frames, and then we're going to go to review. So we're going to talk about first the Paleozoic. Yes, ma'am. Yes, I would like you to write a test question for the material that's before we review, not on the review. So the Paleozoic era is the oldest era that has lots of life in it, abundant life. Before the Paleozoic, the only kinds of life that really existed were, like very simple single cell, a few multiple cell. At the very end, you started to have a bunch of little slithering creatures. But then at the beginning of the Paleozoic, you have a big explosion. So this starts about 543 million years ago and extends about 300 million years. So 543 million years ago, 540 million between friends. This is going back a long time, especially if you believe in short age of the Earth, right? If you believe the Earth is 6,000 years old, 543 million years is completely inconceivable. But that's the date that scientists have for it. And within this era, we have 6 periods, with each one having different kinds of life that dominate. So the Cambrian, Ordovician, Silurian, Devonian, Carboniferous, and Permian, we'll go through those individually. But the reason they're separated is because you have changes in the life forms, new ones appearing. So let's look at, yes. This is actually important. The entire time is dominated by marine life. So shallow seas, we believe, covered most of the Earth at this point. There were some continents. Look at that a little bit. So the oldest, the Cambrian. At the Cambrian explosion, you have some hard-bodied organisms. They're hard-bodied because they're secreting calcium carbonate and calcium phosphate to form an outer skeleton. It's pretty cool, lots of trilobites. And you notice that's about, 50,000 or million years. Then the Ordovician, where you have the emergence of vertebrates, things that have vertebrates. The fish there are jawless fish. I'm not enough into fish to know the difference in a jawless fish and a jawed fish. As far as I know, they all have mouths. And how do you have a jaw or not a jaw with a mouth? But it shows what I know. And looking at paleomagnet, I'm doing that one wrong. Looking at the ocean floors and looking at the magnetic domains frozen into the ocean floors, we can piece together how the continents have moved. And so in this time period, there was a southern continent of Gondwana land. Many people have heard of Pangaea. Not so many have heard of Gondwana land. It's a supercontinent. Pangaea is another supercontinent that occurs later. So the land masses had basically a big continent there in the southern hemisphere called Gondwana land. It was situated close to the South Pole. Then we come up to Silurian, and you start to have a separation. Notice we have here North America, Europe, Siberia are all together. South America is part of Gondwana land in this picture. Very different than looking at a globe today. We have reasons to believe that that's what was occurring. It's not just conjecture. Obviously, nobody took a picture, right? But we still have reasons to believe. You start having terrestrial, that means life on the land masses, not just in the water. So you start to have some kinds of plants, scorpions, and millipedes. By the way, days of creation. Let me just throw in the days of creation so we can contrast. What was created on the first day, according to the Bible? Light. First day, God created light, and it was good. What was created on the second day?
He separated the waters.
The firmament, separating the waters above from the waters below. Well, how about the third day?
The planets or the sun. That's fourth. I feel like that's fourth. No, that's
It includes vegetation.
plants.
Dry land from water. Plants and fishies. Okay, that's our first 3 days. What happens on the fourth day?
That's the moon, stars.
Sun, moon, stars. Fifth day.
The animals of the sea. No, the birds. The birds. And then the animals of the sea. Oh, and sea.
Now I put fishies down here. I think the fishes is there. I might be wrong. I didn't prepare for this before class. I'd have to go read the Bible again. Sixth day. Now that's the end of the creation part. What happened on the seventh day? Rested from labors, which is why we keep the Sabbath day holy. Now, if we look at these, you do see a progression as well as a certain symmetry. We're progressing the first things, plants. I put fishies here. Fish might have been there. Birds and sea animals, and then land animals. If you look at the progressions in the geologic column, they actually kind of follow this order. Now, I don't know of anybody who suggests that the geologic column is mimicking the Bible story, or the Bible story mimics the geologic column. But there are people who believe that the creation story has figurative days, so those days are very long periods. And so one could then kind of fit the geologic column into that belief with little problems. Like, how are you going to have plants surviving for thousands or millions of years of day 3 before you have the sun on day 4? Of course, there's also the inherent problem of how do you have light on day 1 without the sun on day 4? So there's problems either way. There is a certain symmetry. Light is made by the sun. The firmament separating the water above from the water below, making dry air. The birds live in the air, and the sea animals, of course, in the sea. And then on the third day, making dry land, and the sixth day, land animals. So there is some symmetry in this story, which some people use as a reason to suggest that the Bible story is a nice story that is designed with 6 days so that you can have this poetic arrangement. So just throwing that in here, so we can compare it to the scientific ideas we're seeing for time. So after the Silurian period, we come to the Devonian, where we have North America and Eurasia are joined as the continent that's called Laurasia. So there's another supercontinent, Laurasia. And this is the age of fishes when we get to the Devonian. So you have bony fishes, the lungfish, the lobefish. What do I know about those? Next, the Carboniferous. Carboniferous, of course, has the two sections that I talked about, the Pennsylvanian and the Mississippian, the older, Pennsylvanian, the younger, if I remember right. This is when we had a collision between supercontinents. Oh, no! So we have Laurasia and Gondwanaland colliding, making Pangaea. And those collisions cause mountain building. So you have mountain building because of the collisions between those two big continents. And as you see here, present day coal, hence the term Carboniferous with the Mississippian and Pennsylvanian. Finally, we have the Permian. The Permian, you have extinction of 95% of all marine species and 70% of all land species. That's a lot of life that disappeared there. How do we know they became extinct? Well, our answer is simply we no longer see them in the fossil record. And so we assume because we don't see them in the fossil record, they must have all died off then. We also have things that show mass extinctions where you have, like you can find rocks that they call extinction plates where you have lots and lots and lots of fish all there dead together. And then scientists have to conjecture what caused all those animals to die. And so you have things, maybe it's, where you have water and where you have land has shifted and it's changed the environments. Change in elevation. Higher elevation is going to have different oxygen levels. It's going to have different temperature levels, things that are going to make it so different species are more viable. Change in climate. We'll see when we get to the next mass extinction, the KT boundary, that you have believed to be a dramatic change in climate that caused all the dinosaurs to die out. So then we come to the Mesozoic, the age of the reptiles. The Mesozoic has just three periods in it: the Triassic, the Jurassic, and the Cretaceous. And so let's begin. Yeah. Things that survived: true pines and redwoods, flowering plants, insects, reptiles. And so I've already said that. I want to go, I guess I didn't break it up into the separate periods. I thought I had broken up into periods. Dinosaurs are the primary thing in the Mesozoic. You have the first mammals appearing in the Mesozoic, but they are a small component. The end of the Mesozoic is when the dinosaurs died. So they dominated during the Mesozoic and then they died. Why? The belief is a large comet or asteroid that collided with the Earth, and we know where. Within the last 20 years, scientists have discovered that off the Yucatan Peninsula, there is a really big crater. Most of it is underwater. It was found by geologists who are looking for oil. There is some of it above water, but the above water has been pretty much decimated by humans who, instead of letting nature take over and erode and move, have done so themselves, building houses and building roads and whatnot. But there's this really big crater, and if you look in the sediment layers at this boundary where there's the mass extinction, they find shocked iridium. And that shocked iridium, primary source for iridium is from something that is extraterrestrial, something not from Earth. And the shocked is because it had a high pressure shock wave go through it, which changes the structure. Doesn't change the atoms, but it changes the structure. So they find the shocked iridium everywhere on Earth in this layer. And so the belief is that, and that crater dates back to the time of the KT boundary. That's kind of important. The theory is that you had a big collision with a meteor or asteroid hitting the Earth there in the Yucatan Peninsula and causing an enormous amount of material, of dirt and whatnot, to go up into the atmosphere. So suddenly the entire Earth is choked up with this heavy cloud of debris. And so that's going to dramatically change the temperatures. It changes the quality of the air. And so what was before nice, comfortable weather for the dinosaurs, suddenly they can't breathe. They got the asthma. Nobody's got time for that, right? And the temperature changes, so they're probably cold, and they just can't survive. So you have all of these dinosaurs dying. Now, do we still have reptiles? Obviously. Alligators and crocodiles, they existed before this in pretty much the same form. They existed for a long time. So we do have, you can consider, crocodiles, dinosaurs that still exist. So not every single dinosaur was wiped out, but the vast majority were. And, this also says extensive volcanism, which likely would be a result of this impact causing, shifting in the plates. Then we get to the Cenozoic. That's the most recent 65 million years. So that's comparatively only about, 11, 12% of the time that we have life on Earth. And so it's a reasonably short amount of time compared to the entire life on Earth, according to the geologic column. And the Cenozoic, we have Pangea's breakdown. Hence the reason we talk about Pangaea a lot. It's the most recent supercontinent that's broken apart to give us what we have today. It's called the Age of Mammals because you have mammals like you and me that dominate. Feeling better? So you have more mountains formed. The Alps and Himalayas formed, or Himalayas, by collisions of land masses. Ridge movement and plate movement, which caused the San Andreas Fault, which I used to live basically on. What's a fault? It's a crack in the earth. It's not a boundary between plates. It's a crack that's formed elsewhere as a result of the stresses. The climate's cooled. So that's why, we're in a cool time period for the earth because we had changes. In fact, what happens in the Cenozoic, you go to the Pleistocene where you have your ice ages. And of course, you have humans appearing. So that's the end of our material that will be covered on the test. Now we're ready to review. So your potential test questions should be based on up to there. Any questions before I go on to review material? That was a quick run through, right? I don't expect you to have complete mastery of those topics, just a passing knowledge so that you're not ignorant about them. So, exam 3, Earth Science. Hey, let's change colors. It's only going to be over chapters 20 through 23. So, beginning chapter 20, we learned about rocks and minerals, and we learned some really interesting facts about the composition of the Earth. That 8 elements make up 98% of the Earth, or 98% of the Earth. And just 4 of those are almost 93% of the Earth. And just 2 of those are almost 75% of the crust. So you should have a handle on, in the crust, it's dominated by silicon and oxygen. At this point, you can even say why. Why are silicon and oxygen the dominant elements of the Earth's crust? They're the lowest density. Lightest works, the lowest density is more precise. They're the lowest density of those common elements in the Earth. of the big four there, oxygen, silicon, magnesium, and iron, the metals are much more dense. So the crust has the less dense materials because they float up. Hence, the vast preponderance of our rocks are made up of silicates. The vast preponderance are silicates because silicates are silicon dioxide, and those are the two common elements in the crust. So if somebody just gives you a rock and says, what's this made out of? 92% chance you say silicate and you're going to be right for the primary ingredients, not the total, but the primary. If we have silicon and oxygen dominating in the crust, what would we have dominating in the center of the earth? Iron. And you could have said magnesium as well, but there's a lot less magnesium, so iron. Okay, then we have minerals. Make sure you understand what a mineral is, that you can identify a mineral from a non-mineral, and how we characterize them by the crystal form, that is their shape, by how hard they are, by how they cleave and fracture, the one thing, by their color and by their density. You had a homework question that asked, how would you determine if something was a diamond in the field? Throw out to me how you answered that, or what would you try to do? Not bring it into the lab, but you're out there. How would you determine if that's a diamond or something else? Okay, the way it shines, the problem is when you find a diamond in the rough, diamond out there in the dirt,
No.
you're not going to have nice surfaces to shine.
Wait, are you talking about like physically?
Yeah, what can you do if you're, let's say you go out.
Yeah.
Okay, scratch it. Scratch it is the first thing we think of. And if you try to scratch it, if it will scratch, then it's softer than the thing you tried to scratch it with. Well, diamond is the hardest common material, so you won't be able to scratch it. You know what the problem is? The hardest thing you're likely to have with you is a hardened steel knife blade. And the hardened steel knife blade won't scratch sapphire, won't even scratch quartz, I don't think. So it's really not going to help you very much. It'll scratch, I think it'll scratch glass. So you can tell the difference in glass and diamond. But you couldn't be able to tell, I say it'll scratch glass. Quartz is mostly glass. Or glass is mostly quartz, so I'm not sure about that. But the scratch test, as wonderful as it sounds, isn't going to be very determinative because a lot of the things that look like glass are hard to scratch. They're hard. So I actually, after I wrote my answer, I went and looked online to see what experts say on how do I identify if it's a diamond. And they said, scratch test, you're never going to figure it out in the field because there's too many things that you won't be able to scratch. So then we have to go to other things. Did you guys come up with something else, or did you all go with the scratch test? It's the obvious one, right? It was my go-to. It's my first. I listed like three. I don't know how many people looked at my solutions, but now you know they're there. I think I listed 3 different ways. Color, the fracture, the symmetry is what I actually went with, is the one that would be definitive. If I look at it and I see that it has a hexagonal structure, then that's going to help me to identify it's either quartz or sapphire. And so if it has, a pyramidal structure rather than hexagonal, then I can say, this probably is a diamond. And the chances of that are like worse than your chances of winning the lottery. But go for it. Crystallization. Another question you had in the homework was about determining, you had pyroxene, olivine, quartz, and I can't remember the last one. And you were asked to determine which one is going to crystallize first and which one will crystallize last. Well, the key to answering that question is the silicate content, or the silicon content is what it says in the textbook. So once again, if you looked at the solution, you'll see that I actually went and I said, okay, it has this much mass silicon, this much total mass, so it's this % silicon for each one. And then you just rank it by how much silicon it has, if it's going to crystallize earlier or later. So quartz with the most silicate because it's silicon dioxide, it's going to be the last one to crystallize. The one with the least silicon is going to be the first one to crystallize. So rock types, igneous. Igneous means fire formed. Igneous rocks are molten rock. Now, this has 3 different types. I probably won't ask you about these, but I will remind you right now. Granitic, very slow cooling. That you need to know. Basaltic, fast cooling. What difference does it make how quickly it cools? If it cools quickly, there's no time to grow very large crystals. In fact, if it cools super quickly, it's not even basalt, it's glass. Super fast cooling rock is just glassy because it doesn't have crystals formed. If you have it slowly cool, you grow bigger and bigger crystals, and that's what granite is. Granite is big enough crystals that you can look at the granite and see, there's a black crystal, a mineral, and there's a pink crystal, a mineral. And you can see the different crystals that have grown large enough. So that's the difference in those types of rock. Sedimentary rock, you've had some kind of erosion. Well, first it starts with weathering, then erosion. Let's make sure we differentiate those, because I'm pretty sure you're going to have that on the test. What is the difference between weathering and erosion?
Weathering is the breaking down, and then erosion is distributing it.
Yeah, weathering is breaking it down. Can occur by mechanical methods, abrasion, rubbing, chemical methods, dissolving chemicals. That's weathering. Erosion is transporting it to a new location. And then you have the deposition, dropping it out. Deposition usually occurs going from faster water to slower water. And then cementation, compress it, and some chemicals like calcite will harden, making it into a rock. And finally, there's metamorphic rock. Metamorphic rock is rock that's been heated and put under pressure, but has not been fully melted. So it's deformed and squished. It's like you put it in a toothpaste tube and you squeezed it out. It never actually melted, but it got deformed. Now, volcanoes, we didn't talk about shield or cinder cone, but we talked about them nonetheless. The Hawaiian Islands are shield volcanoes. They're called shield volcanoes because they're rough, they're pretty flat. They look like pancakes. They don't have big cinder cones on them. The difference in those, though, a hot spot where you have magma coming up from deep, that magma usually flows reasonably well for magma. And if it flows reasonably well, it comes to the surface and just flows out, making the flat shield shape. Where you have convergent boundaries, you grind the rock, that ground rock that melts, floats up and makes volcanoes. That rock usually flows much more poorly. Why? Because of different mineral content. Or actually, mineral content. If it's molten, they're not called minerals at that point. But it's chemical content. And so because it doesn't flow well, it basically forms a blockage, a dam, and you have to build up more and more pressure underneath, and then it breaks with a dramatic explosion, an eruption of the volcano, and that explosion then leaves debris more close to the crate or to the hole where it came out, less farther away, which is what builds up the cinder cone. So the cinder cone is what you see primarily at convergent boundaries. The shield volcanoes are what you see at hot spots or at divergent boundaries where you have magma from the deep that's flowed up. And composites are just somewhere in between because nothing is perfect. Okay, the sedimentation process I've already talked about. Sedimentary rocks, we classify them by the types of material in them. Bigger material would be something like a conglomerate or a breccia. The difference in conglomerate and breccia is simple. Conglomerate, which is what the sample was that I showed you, you have smooth pebbles. rocks cemented into the rock. That's a conglomerate. So, like, if it was natural instead of man-made, a cobblestone road would be conglomerate. Breccia is where you have sharp edges in the rocks instead of smooth ones. We see that on the moon. So breccias form when you didn't have water causing the rocks to tumble, because if you have water causing the rocks to tumble, it smooths them. So that's, breccias are definitely not formed from flowing water. Conglomerates are. Grain size, if you get smaller, you have sandstone. Smaller still, you have shale, mudstone, and can't remember the last one. But based on the size, you get smaller grains. It packs more. Oh, clay. Yes, clay. It packs more with the smaller grains. That means it has less porosity, less holes in it, can't hold water. And also, usually less porosity means that you have less permeability. Water can't go through it as well. Metamorphic rocks, we did not talk about the foliated rocks at all. So the other stuff we've already mentioned. The rock cycle, I've already gone through the pieces in the rock cycle. Remember, there was the circle with the different pieces in the picture. Going to chapter 21 in plate tectonics. One of your homework questions was asking you about S waves and P waves. And what are they? They're seismic waves. Actually, one of your homework problems, that was one of your quiz questions, wasn't it? Yeah, it's one of your quiz questions. They're seismic waves. They're waves that travel through the earth. They're not just surface waves, right? The picture here clearly shows them going through the earth. But notice the S and P's come out here. Nothing comes out there, and then it's only P's here. P waves, pressure waves or primary waves, can travel through a liquid or a solid. S waves, shear or secondary waves, can only travel through a solid. Okay. Pressure can be a liquid or solid. S waves can only be through a solid. And so the fact that we only have P's in the region down at the bottom tells us there must be a liquid portion to the earth. So that's our scientific reason to extrapolate. And then based on where we see this shadow zone, we determine what the radius is for the liquid portion. And then we say there's a solid core inside, because that solid core inside is going to make surface waves that we can see again. Surface waves are Love and Rayleigh waves. Love and Rayleigh waves are combinations of S and P waves that occur on the surface of a material, on boundary. So you should know the order here: the crust, the mantle, the outer core, the inner core. There's really not much point in differentiating the upper mantle and the lower mantle, because you know what? It's impossible to get those wrong, right? Who's going to say, oh, well, we have the lower mantle on top and the upper mantle on bottom? Like, no one's going to say that. So that's not important differentiation. Know the theory of plate tectonics, that we have these plates that slide over the surface of the earth. And what drives that motion is the magma pushing up into the rift zones, pushing the plates apart. And so we have the divergent boundaries where we have the rift valleys. That's supposed to be valleys. It says values, doesn't it? Very nice. The rift valleys, such as, have you guys seen articles in the last week about a big rip occurring in the ground in Kenya? No? Well, it's very much a drama. Putting drama to something that doesn't have drama. There's a rift zone in Africa that it's believed in 1 million years or so will actually result in separation enough for water to flow in, having a low region with an ocean building up. And so Africa's splitting. It's going to form another small plate there where it's separated. So we have one rift valley that is on dry land. All the rest are in the middle of oceans, because the density of the basalt that's produced with this rifting is higher density, thus it sinks lower. Convergent boundaries, where you have subduction, one sliding under the other, it's going to be the ocean plate sliding under the continental plate. It causes grindage. That's Pauly Shore's word for food, by the way. Causes grinding of the rock, which melts it, floats up, makes volcanoes. But that pressure also will cause stresses in the earth, which will make the earth crack. The places where the earth cracks, we call them faults. And where you have slipping on those cracks, we call it an earthquake. Also causes crumple zones. And I've talked about what's our crumple zone that's near us here. The Rocky Mountains, right? The Rocky Mountains are a crumple zone where the continent has crumpled up because of the, we call it compressive stress created by the subduction of the Pacific plate under the North American plate. Now, right now, the Pacific plate is not subducting under the North American plate. It's right now a transform boundary. Transform boundaries are where you have, like the homework problem we just looked at, the Pacific plate is moving north compared to the North American plate. That's a transform boundary. They're sliding like this. That's not going to result in much earthquake. Or not much earthquake. It's not going to result in much volcanoes. It will result in earthquakes still, but not volcanoes. Okay, water. Yay. We're getting to recent stuff already because we only have 4 chapters we covered. 71% of the earth is covered with water. Oceans are important to us. 97% of the earth's water is in oceans. I keep meaning to correct myself. I was talking to my wife and I said something else. But to you guys, I think I never said it wrong. 97% of the earth's water is in oceans. Of the remaining water, almost all of it, 2% of the total of Earth's water, is frozen. Now you can see rounding. 1.5% remains. It would be 1% if there wasn't rounding, right? 1.5% of the Earth's water is then liquid and not in oceans. And of that, 98.5% of the 1.5% is underground in aquifers. Aquifers, underground water. And that was the number I told my wife. I said like 98% of the Earth's water is in aquifers. It's 98% of the available water to us is in aquifers. In case you want to go to my wife and tell her, hey, your husband was wrong. He told you this and it should have been that. So the amount of water that's surface water and not oceans is very, very small. We look at the Great Lakes and we're like, woo, that's a lot of water. But compared to the water that's under the surface, it's not much. The hydrologic cycle, remember we had the picture showing the evaporation. Water goes up into the sky, precipitation, it falls back down. You have runoff where it runs back into things like the ocean, and infiltration where it flows underground, becoming part of the groundwater. Groundwater is stored in porous regions. Porous regions means that you have holes that water can then be stored in. So make sure you know the difference in porosity and permeability. Permeability is how easily water can go through the soil. Porosity is how the volume of holes compared to the volume of the rock. Usually, highly porous rocks are highly permeable. That is, if they have lots of holes, usually water can flow through them. But it's possible to have a porous rock that water can't flow through. An example of that would be something like some forms of pumice. You have lots of air bubbles that are frozen into a rock. But if the air bubble has rock all the way around it, no water can flow into that air bubble. And so its porosity is high because it has lots of air bubbles, and permeability is low because the water can't flow through it. That's not going to make a very good storage for water because you can't get the water to flow through it. The water table is the dividing line between saturated and unsaturated soil. If you're going to drill a well, you want to drill down into the saturated soil. And you want that soil to be a high enough permeability that the water can flow into your well. If it's non-permeable, it's not going to help you because you pump out the water in your well and there's no water to replace it because it doesn't flow. Artesian wells and springs, remember we talked about artesian is where the water just comes up out of the ground. Why does it come up out of the ground? Because you have water at a higher level over here that's creating pressure that pushes the water up and out of the ground.
Is that the same thing as the limestone thing you were talking about? Oh, which one related to the, not limestone, sorry, that one colorful place where the guy fell in?
No.
Okay, then which one is that?
That was just, I was talking about cyanobacteria and talked about the Yellowstone hot springs. Okay, perched water tables, remember that's where you have an impermeable rock, and on top of that impermeable rock, because it's impermeable, you have some water that's sitting there. So that's perched because it's not below the water table. It's a saturated soil that's above the water table. And the hydraulic head is telling you the height difference between the water level and where you are. Or a reference point, I should say. Problems that occur with water, subsidence. That's what we saw in California's Central Valley. Because water has been pumped out of the aquifer, the water was helping to hold the soil apart, keeping it permeable. But when you pump the water out, the soil can collapse down, and then the ground becomes less porous and less permeable, and thus you're going to have a really hard time getting it to come back up. So the subsidence is pretty much permanent. You pump the water out, the ground sinks, and now it's permanently down lower. So that's a problem because then you can't replenish the water once it's subsided. If you dissolve carbonates, if you dissolve limestone, you had stone that was holding up the ground. You dissolve it away and you no longer have stone holding up the ground. The ground collapses, a sinkhole. And that's problematic, as I said, especially if it happens where you have your museum with Corvettes in it in Kentucky. We talked about streams. Water will cause erosion. You'll have more erosion where the water is traveling faster. Deeper streams, water travels faster. If you have a bend in your stream, the outside of the stream is going to be eroded. The inside of the stream is going to have slower speed, and so it's going to deposit. And so that causes your streams to change their paths over time. If you have a relatively flat region, then your stream will meander across that region, creating a meander valley or floodplain. Sometimes I can't read. I read this as faster water erodes. Like faster, or I read it as freshwater erodes. Freshwater erodes, that doesn't make sense. Yeah, the faster water moves, the more material it can carry with it. And so it's more likely fast water will pick up material and carry it. When it slows, it doesn't have the energy to keep carrying the material, it drops it back out. And so that speed of the water has everything to do with the erosion and deposition. Make sure you understand what the continental divide is. The drainage basins, water drains to Pacific Ocean or to the Atlantic Ocean. Continental divide is the separator between where the water is draining. And deltas, that's where water from a stream hits non-moving water and makes a big deposit there that usually has a fan shape, which is where we get that delta name from. And streams carve out V-shaped valleys. So if you look at a valley, it's got a V shape, you can say, wow, that was probably made by a stream. Glaciers, on the other hand, it's a glacier if it doesn't completely melt. You put down snow, over the course of a year, not all of that snow will disappear. So then it's a glacier. Some flow, some don't. They create U-shaped valleys because the entire glacier is sliding, grinding the ground. It's not just eroding in the center where the water is, it's eroding over the entire range of the glacier. Accumulation is where you have snowfall. Ablation is where you have sublimation, where it's going from the ice into the air. Moraine is that debris that's ground up. And then we had eskers, drumlins, and till. Eskers are the little paths for streams that were flowing under them. Till is the moraine that gets pushed ahead of it. Drumlins are they're little potholes, I believe. And the final thing we talked about was sand dunes there. And then we don't have time to talk about chapter 23, but that's okay because this here we talked about in class on Monday, and then this we talked, well, actually the radiometric dating we talked about a long time ago, but we talked about this stuff today, and that's the end. We're not going to talk about chapter 24 or beyond. Okay, we are out of time. I will see you for lab tomorrow.